what you need to know about paper chromatography. Okay. Here's the idea. Right? So nothing is due from this, but the ideas behind paper chromatography are really important ideas. Okay? Especially in terms of lab techniques. So for you, because I canceled lab, nothing's due. This is just a review for the final. That's awesome. I will give you a little bit of work that you may want to do, simply because it would be great prep for the final, but that's totally optional, okay? So just as an FYI. But if you have the joy and bliss of going on in chemistry, chromatography is this major principle that we use over and over and over again. So if you guys would turn in your lab manual to page, I think, 44, 43. It's one of those. 43. 43 is the magic number today. You will see two chromatographs, right? So you have two, you have a top and a bottom. Those two charts that you see there are called chromatographs. They are from a GCMS. Actually, it's from a GC, the way they're shown, right? And when you look at these, and you see that they have peaks on them, and you're wondering what those peaks mean, okay? So that's the idea of what we need to talk about, okay? So for paper chromatography, you know that, let's talk about what would have happened if you had done this really well. Does that sound like a plan?
Yes.
Yeah, so if you had gotten results that were awesome, here's what they might have looked like. And y'all might thank me for not doing this lab because it's a very Goldilocks kind of lab. In other words, you can't do it too much or too little. You have to do it just right, which is a lot for the second week of class, or the second experiment. So in terms of doing this, what you would have done, as you know, because you read the lab in advance, right? You would have marked a line right here that you would have dotted some solutions on, right? And if you had been wild and crazy, you might have actually marked which solution you were putting on each of these, right? And say that you put it in this order, right? So the standard is here, and the unknown is here. Okay. And the dot was really what you were looking at in terms of trying to make it just right. Okay. So, and you folded them into 3 pieces. Now, if you had done this really lovely, then what you would have gotten is you would have gotten a series of, and this is at the very end after all of the visualizations, right? You would have gotten this kind of idea when you had it in the chamber of it looked like water was moving up the paper. That's kind of the idea. Okay, the water moving up the paper is where the mobile phase came in, right? So we have these two ideas here of stationary phase and mobile phase. Okay, so does anyone know what the stationary phase was in this particular case? Oh, I so missed. It's okay. Guesses? Wild guesses? Stationary means it stays put.
The stationary phase is when the ink crosses it in and it's the movement of the element, right?
Actually, the mobile, both of these are appropriately named, right? A mobile phase means it moves something.
Yeah.
Stationary means it doesn't. So,
Yeah,
what was the stationary phase in this case?
So when it's done moving?
That's I'm thinking of a. It's an awesome thought. It's something that you used. It's one of the components of what you used. When we talk about a stationary phase, these are things that we are using to make our metals travel up the paper or do whatever. Okay. So the solvent was another name for the mobile phase. So I'm going to go there since you guys are kind of going there. I really like all of the things that you're saying. And all of what you're saying is about the mobile phase, so that's awesome. Okay, so the mobile phase makes things move, right? And in this case, this was acetone and HCl, right? So the acetone and HCl, what you put in the elution chamber that made things move up the paper, okay, is what the mobile phase was. The stationary phase in this case was the paper itself, right? All right, so what's happening here? Okay, what actually happens in the midst of this particular lab is something that you probably did as a child, or something close to that, or even more recently if you just decided to do it. Okay, if you got really good paper towel, and by really good paper towel I mean something like Viva paper towel, right? Because it is more like filter paper, and you put a little X of like a Crayola black marker at the bottom of that, and you put it in water. The water wicks up the paper towel, and you see colors spread out. Okay, exact same idea happening right here in this experiment. Okay, so when you looked at the mobile phase traveling, you could actually see it wick up the paper just like you would have done with the paper towel. Okay, and when it was about an inch from the top, you would have marked it and said, "Oh, there it is," and then you would have taken it out and dried it out, and then you would have done a couple of different visualizations to make sure that we could see it, see the dots that had moved. Okay. The idea here is that when you did this, okay, if you had done all of the visualizations that they all turned out perfectly, what you would have seen is you would have seen iron travel with the solvent, right? Which means that it's going to travel with the solvent over here. Nickel would have been at the very bottom, right? So you would have had nickel. Actually, I'm going to do this here. I'm going to do it in black, not brown. Right? Cobalt somewhere kind of in the middle, and copper somewhere kind of in the middle. Okay. Okay. So the idea here, that may be a little bit too high. Sorry. Ooh, let's make it a little lower. Yeah, there you go. Okay. So what's happening here is that with the specific metals, right, when you dot those solutions, you would have just gotten a dot for each one. Okay? We can already tell that iron liked the mobile phase. It liked the acetone and HCl. That's why it traveled with that phase. Okay? So in terms of looking at this, iron is about an RF factor of 1. We'll talk about what that means in a minute. The Ni didn't like the mobile phase, right? You dotted it right here, and it moved to right there, okay? Because Ni didn't like the mobile phase, it actually liked the stationary phase better, okay? And when you did this standard, when you did a mixture of all of them, if you had gotten really awesome results, you would have gotten something like this, right? Where you would have seen distinct space between each of the dots. Okay? Now, having said that, does anyone ever get that in this lab? I think I've maybe gotten it once. In the history of me doing this lab. I think one person, one time, got it to be really nice and clear like this. Okay, so it's probably not going to happen. Okay? When it is really nice and clear like that, we say that the dots have good resolution. So there's space between them, you can tell which one is which, so on and so forth. Okay? This idea of getting in your mixture, having some things like the stationary phase better and some things liking the mobile phase better is the art of chromatography. That's the whole point, folks. You want in any chromatograph or any chromatography mixture that you're using, that you want some of them to like the stationary phase better so that they come off later, and you want some of them to like the mobile phase better so that they come off sooner. Okay, and this is true for any chromatography. So you've heard some of these acronyms before if you watch any CSI type shows, any of these kinds of shows. In fact, it's so ubiquitous that I hear it on random shows and I'm like, okay. Right, so like GCMS, GC means gas chromatography. Right, MS is mass spectra, that's a way of actually analyzing the components as they come off. HPLC is high performance liquid chromatography. Chromatography is everywhere in chemistry. Let me just put it that way. And this idea of mixing stationary phases and mobile phases is actually the point of all of it. Okay? Also, and you do that in order to achieve great resolution. Be able to tell which one is which. Okay? If I had done this and I had added an unknown, right, I would have been able to say immediately, if I had had, for instance, this and this, right, then you could say that in that unknown you had what two metals? Iron and
Cobalt.
cobalt. Okay, so you were basically playing match across the paper. Okay, but that was the idea behind paper chromatography. Now let's look at page 43. Right? So page 43 with these awesome chromatographs that you have here. And notice this is a drug screen, right? And then you have some chlorinated pesticides. The EPA uses this, NIST uses this, all kinds of groups use this. The Coast Guard uses this to do drug tests, right? Steroid usage is based off of this idea. So just FYI, used a lot. Okay, so having said that, look at the top chromatograph there. You can already tell where at least 3 times, and there's one that's particularly bad, where good resolution was not achieved, right? The instrument is smart and was still able to label it, but it did not have the greatest resolution ever. Can anyone tell me one set of numbers that's one of those times? 3 and what? It'd have to be a set of numbers, right?
5 and 6.
5 and 6. 5 and 6 are pretty close together, right? There's not a lot of space around those. So the machine is smart and understands that those are 2 different things, but especially because they come from the same beginning. If you look at the bottom of that chromatograph, right towards the line that's going across, they start with the same, they're like the same peak, but they're split into 2. Okay? That's not awesome resolution. You'd want as much space between those peaks as possible. Okay? Like I said, the machine is smart. It can figure it out, but that's not awesome resolution. Tell me another time. 9 and 10 is very much the same idea. And then the last time, which is the worst? 13 and 14, right? Look at 13. It's almost embedded in 14. Right? Like I said, the machine is smart, or the person who's doing the machine is smart and knows what it looks like. But indeed, that is not great resolution when you have a peak embedded in another peak. You have no idea what's going on there, unless you just happen to know that, and it's a distinct peak that you see a lot. Okay, do you see what I'm saying there? So those are not great resolution. 3, and go back to 3 for a moment, 3 and everything else is awesome, right? Because that has a lot of space between it and everything else, okay? In terms of the key resolutions achieved, for those of you who are like, well, that lists all of the ones that we talked about, it's not talking about between 5 and 6. It's saying that between 4 and 5 and 6, there's great resolution. That was important resolution to have. So the ones that are spaced out a little bit more is what you're looking at in terms of key resolutions achieved. Does that make sense to folks? You got a sense of what's going on in terms of chromatography? Okay. If you were going to practice things for the final, what you would do is you would look at page 53.